So the first concept that I want you to know is interpretation and valuation. And this is the definition. So first, we have propositional signature like PQR. And now we start to talk about the meaning of the formula. So we have two truth value symbols called false and true. And note here that this is not a part of the formula. Okay, they are in the meta level. Okay, they are meanings of the formula, but you are not supposed to use F and T as part of the formula. Okay, now what is special about it is we are going to talk about so-called interpretation. This is a mathematical object that we can give meaning to the formula. So basically this interpretation, mathematically it is a function from signature to truth values. Okay, so if you have atoms like PQR, then P can be mapped to one of the two values, true or false. Q can be mapped to true or false, and R can be mapped to true or false, right? So each of these mapping is called a function, is an interpretation. So the question is, how many interpretations are there for PQR? How many interpretations are there? How many functions are there from PQR to truth values? 6? 9? 8? Yes, 8 was actually the midterm problem, right? So we had 3 elements in the domain and 2 elements in the range. So then you have 2 to the power 3 functions. So basically this is same as what you already know. It's just a function. We just give the name interpretation to this special case of functions where the domain is a set of atoms and the range is truth values. But it's basically just a function. Okay? So there are 8 functions. And you can think about each of these functions as a possible way to understand the world. So in some world that P can be true, in some other words, P can be false. Okay, remember the taxi example. So in some world, taxi can be late. In some world, taxi is not late. Train was late. Train was not late. John is late, or John is not late. Okay. So those are the possible interpretations. Possible way to understand each symbol to be the true or false. So there are 8 possibilities. That's the whole possibilities. Okay. So if you imagine that PQR represents some particular fact about the world, in this case, you're only considering 8 possible worlds. Okay? So that's one thing. The other thing is there is some special table that is associated with the symbols. So if you have negation symbol, this is also a function. Okay? This function negation takes the truth value as an input and outputs another truth value. Okay? Again, this is a function. Okay, so for this negation function, it works very special way. If you give true, it returns false. If you give false, it returns true. Now note here that this, I don't want to confuse too much, but this negation function is not the same as negation as in formula yet. Okay, in the formula you can put a negation in atoms or some part of the formula, right? This negation is actually a function. It's not a symbol in propositional logic. It is taking an argument of truth value. So they are actually syntactically different. Okay? Now for the conjunction, disjunction, implication, equivalence, they all have also the associated truth table. And maybe you have seen this table before. If not, don't worry, because this is basically very intuitive to understand. So if you can take X to be true or false and Y can be true or false, how many interpretations are there? 4, right? So false, 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 true, true, false, true, true. These are the all possible combination. Now for the conjunction, it's same as in English sentence and, right? So for this one, if you look at this, it's only one case that is true. When both of them are true, only in that case the conjunction returns true. Otherwise, it returns all false. Right? Because that makes sense. You have to do this and that, okay, if you did only one, that you didn't actually fulfill the end statement. Similarly for the or, okay, in the case of or, when this is false, it's only when both of them are false. All other cases, it is actually true. Okay, so same as you can play outside if you do this task one or this task one. Okay, then usually people try to do only one task. But anyway, that does not matter because you fulfill the or condition. So this is easy. Now the most difficult part I observed for 15 years of teaching in the ASU. No, 14. This one, implication. Implication is the most difficult because it does not actually convey your intuition well. It may seem to be, but there are many cases students are confused and they cannot actually understand. I cannot explain why. So here's the thing. Let's actually look at this, the definition. This is a definition, so it's useless to argue about why this makes sense, right? But so the definition-wise, it says the implication can be only false when X is true and Y is false. So true implies false is false, but all other cases, it is actually true. Okay? Now, obviously, people say that, well, true implies true is always true, right? That makes sense. But what usually people don't get is actually when false implies false, why is it true? Okay? So I'm not going to answer this question now. When you go through this, we can come back to this issue. But for now, I want you to just take this for granted. So when X is false, okay, we are going to do some exercise problem today, and hopefully that nobody gets confused about it. When X is false, then regardless of what you have for Y, X implies Y is always true. Okay? Okay? So let me tell you the precise answer I can give you after I go over the soundness and completeness theorem. And that's probably next lecture. If you just want to have a quick idea why this is the case, then it's similar to the natural deduction. When you have false bottom, then you can derive any formula. Same as that. If you have false, then you can say anything about the Y. It has some analogy there. Okay? If somebody makes nonsense, then this sentence is always true. Okay? All right. So that's interpretation. Interpretation is just a set of possible ways to understand the symbols, true or false. But it doesn't talk about the formula yet. The formula is an arbitrary complex composition of symbols using the connectives. So when you say a valuation of formula, now this means that each formula can be mapped to true or false, depending on which interpretation that you apply. So let's look at this example. Okay, so P implies not Q, implies Q or not P. Actually, is that the right one? Yeah, okay. So how do we evaluate this formula? So we can, so usually people draw a so-called truth table. Okay, so PQ, and PQ can be false, 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 true, true, false, true, true. Okay, and then apply these to more complex formulas. Okay, so let's work on not Q. Okay, so not Q. Remember the negation function. What is it doing? Okay, so when you have negation, then false turns to true, true turns to false, false turn to true, true turn to false, right? Okay, and then you also build up another one, P implies not Q, okay? So let's do this together. P implies not Q. So you look at this guy, false implies true. Is it true or false? Somebody say false, it's not that. So this is actually true. Again, this is one case that I want you to be cautious. Okay, next one. Is it true or false? So next one is false implies false is actually true. Next one? True. Next one? False. Okay, good. Now, the other thing is Q or not P. So let's do not P first. Not P flips the case for P. So this is true, true, false, false. And then now let's talk about Q or not P. Okay, so look at this column and make a disjunction. What do we get? True, 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 false, true. Okay, so just look at the two cases, and as long as what you have at least one true, then the returning value is true. And then we can now talk about P implies not Q, and Q implies not P. Okay, so now look at this column and this column. Okay, so true implies true, true. True implies true is true. True implies false, false. False implies true, true. So this is the final table. Actually, I wrote this lengthy formula, but it seems to me that I could have written a simple formula that shows the same behavior, right? What could be that formula? So what is the simple formula? Instead of this guy, I can write here so that I can return true, true, false, true for the combination of PQ values.
P implies Q.
P implies Q. Yes, P implies Q. And not somebody say Q or not P, that's also true. Okay? So what you see is when you're given the formula, you can write one truth table. On the other hand, when you look at the truth table, you may have more than one formula that match this truth table. Okay? All right. So let's practice this together. Okay? So I show you the complete picture, but sometimes often when you are given a particular interpretation, you want to evaluate. The way that you do is just parsing. Okay, so you look at this thing and then try to do in a bottom-up way. Actually, let's do the first problem together. So here P is true, and Q is true, and R is true. Okay, so the valuation here, the formula is actually what is the value in the root node. Okay, so we are going to compute this in a bottom-up way. So suppose you have this true. By the way, this is the same example that we talked before when we do the parsing the propositional formula. Okay, so if you are not familiar with how to convert this formula into tree, go back to the lecture and make yourself familiarized with this concept, because we are going to do this satisfaction checking a lot. Okay. So I want you to do this, gain some skill here. So if this is true, then this guy is false, right? Okay. And Q was actually true here. So I can actually copy all the truth value in the leaf node. Okay. And this node is false and true. So this becomes false. Okay. And at this point, I don't actually care, right? But let's actually do this bottom up. So this guy is true and false. So true or false is true, and this was true and true, this is true, and this is false implies true, which is true. Okay? I just did it in the bottom of A, okay? Using the table that we saw earlier. Now, again, false implies true, okay, is the tricky case, right? I said in the middle that I don't need to actually look at the right subtree, because if the left subtree is false, then whatever that you have on the right subtree, false implies anything is actually true, right? Okay. So the answer to the first question is actually true. Okay, so it's a good time to do the next one in Socrative. So this is true-false question, and see how many of you can get this right. Okay, start it. So the second problem is when P is false, Q is true, R is false. So P is false, Q is true, and R is false. So this is the case. Okay, are you ready to close? Okay, so let's open. Two people didn't submit. Now only one person didn't submit. If you constant, yeah, okay. So the majority was false. Okay, so okay, so that's the majority. Not sure what happened to the 17%. The answer is false. Yes, why is that? That's the case. Let's look at this together. So when this is false, this returns true, and true is true. Okay? Now when you look at this guy, this is false, so this is true. True and true is true. False and true is false. True implies false is false. Okay? So this is true. This is false. Okay, for the third problem, I will give you an exercise problem. Not too difficult, but you should be able to do it by yourself. Okay? Right, so using this notion, we are going to can talk to your neighbor. Okay, so let's close. So actually, many of you chose 1 to be a tautology. Also included 2. Some students also said 3. And some of you honestly said, I don't understand. So I appreciate that. Okay, so let's do this together. So what I ask you to do is, when you look at this one, okay, how many interpretations can you apply? How many interpretations can you apply to check this is a tautology? 4, right? So P is false, Q is false. False, true, true, false, true, true. Okay? So I actually ask you to do 4 checking for problem 1, another 4 checking for problem 2, another 4 checking for problem 3. So I just ask you very CPU intensive job. Okay? So you have to do 12 valuations. Okay? And surprisingly, many of you actually did well. So the correct answer is 1 and 2. Okay? So they are tautologies. Okay? Now, if you apply the truth table, as I just said, you're doing the 12 valuations checking. Okay? Now, you may have noticed that 1 and 2, all of them returns true. Okay? If not, let me know. If some of you got false for 1 and 2, no. Okay, so now for the third one, this is not a tautology. Okay? So what is an interpretation that makes this formula to be false? If it is not a tautology, by definition, that means there is an interpretation that makes this formula to be false. So what is that interpretation? P is true, Q is false. Yes. So if P is true, so this is true, false, right? So true implies false will give you false. Again, true implies false, give you false. Okay, I didn't draw the path tree, but if you mentally draw it, you can evaluate in a bottom-up way. So the third one is false when P is true and Q is false. So this is not a tautology. Okay? So the correct answer is 1 and 2. Now let me ask you this question. What would be an easier task? To check that the formula is a tautology or to check that the formula is not a tautology? Which one is easier? Not? Who said not? Okay. So it seems like that's the case, right? If you are checking this is not a tautology, then all you have to do is to find one example that makes the formula to be false. Okay? However, the complexity of these two problems are actually the same. Okay? Because so suppose you want to apply that to the first formula. So you want to check that this is not a tautology. Right? You want to find an example that makes this formula, the first formula, to be false. How many cases that you have to consider? One? So which one is that?
Because of the way implies works, you
Yes.
know that it will only be false if the first one is true and the second one is false.
Right.
So you try to reason
Can you?
out a way to...
Right. So how many interpretations do you have to apply to find that one? There are 4 interpretations, right?
Yeah.
And how many do you have to try?
Yeah, all of them, I guess.
All of them. Because none of them actually give you the one that you want, right? So in order to find it, you have to go through all interpretation. But nonetheless, if you're lucky, then like the third formula, you can say this is not a tautology. So in practice, if you want to check something is a tautology or not, that's a good idea. Try to find an interpretation that makes the formula to be false. That's a good way to go. Okay? If you try hard and if you cannot find it, you will find yourself ending up enumerating all interpretations. Okay? And none of them give you the formula to be false. That means this is a tautology. Okay? All right, good. Next one. So, like tautology, satisfiability is also similar in the sense that we don't need to talk about a particular interpretation. By definition, we say a formula is satisfiable if there is at least one solution. If there's at least one interpretation that makes the formula to be true, then we say this is satisfiable. Again, we are applying the same thing here. So let's do this quiz. So what I'm saying is, your task now is to say that this formula is satisfiable, meaning that can you find at least one interpretation that makes the formula to be true? This is not the same task as the previous one, right? In the previous one, you have to find all the formulas that evaluate to true for all interpretations. But here it's actually for some interpretation. Okay, so let's do this together. The first one, is it satisfiable? Yes? Somebody say yes. What is an interpretation? Somebody said yes. It was a tautology, and every tautology is satisfiable, right? So every tautology is a satisfiable, meaning that tautology means that for all interpretation that the formula is true. So that obviously satisfies the condition. There is some interpretation that satisfies the formula. Okay, so it's obvious. Tautology has at least one interpretation that makes it to be true, right? So this is satisfiable. You can actually choose, say, PQ to be true, right? So true implies true is true, true implies true is true, so the whole thing is true. Okay, so that's yet another way. And similarly, for the second one, this is also satisfiable because if you apply true to PQ, that's also the case. Okay, what about the next one? If I say true, true, will that be true? Let's play that. If I say PQ is true, okay, is this formula true or false? False, right? If I say P and Q are true, then the antecedent here is true, but this one is actually false because Q is false, conjunction with true is false, so true implies false is false. Does that mean that this is not satisfiable? No. It simply means that I was unlucky that the interpretation I tried was not the one that we are looking for. There could be another interpretation that can satisfy this formula, that can make this formula to be true. So having one interpretation tried and it doesn't make the formula to be true doesn't mean that the formula is not satisfiable. There may be some other interpretation that makes that to be true. Okay? So if you make, let's say, Q to be false now, what happens? P is true, Q is false, right? This guy is false, and false implies anything is true. So this is this interpretation that makes the formula to be true. So we found one interpretation that makes it to be true. All right, so let me now ask you a similar question. Which task will be easier to check whether the formula is satisfiable or not satisfiable? So for the satisfiable, meaning that you need to find at least one interpretation that makes the formula to be true. If it is not satisfiable, meaning that all interpretation that you tried, all of them fails. They make false. So which one is easier to check? And that goes back to the same argument. So conceptually, if you're lucky, then you can find satisfiability easily. But if you're not lucky, ultimately you are going through all possibilities. Okay? So note here that the difference between these two, if the formula is not a tautology, then you only need to go for one interpretation that makes the formula to be false. And if you're lucky, you may be able to find that easily. In the dual case, the satisfiability, if you're lucky, you can find the interpretation that makes the formula to be true. Then you are done. Okay? The reason that I'm telling you this is we will get back to the relationship between these two. So some of you who are smart enough already get some idea how these are related. Okay. The notion of satisfiability can be extended to a set of formulas. So before we talk about single formula is satisfiable or not, but we can also talk about a set of formulas to be satisfiable or not. Okay? So the definition is saying that a set of formulas is satisfiable if there is one interpretation that makes all formulas in the set to be true. Okay? And if you cannot find such a formula, such an interpretation, that means this set is unsatisfiable. Okay? So, here's a question. Is this set satisfiable? Can you find at least one interpretation that makes both formulas to be true? Is this satisfiable? Now let's do the Socrative. This is true-false question. So can you find an interpretation that makes both formula to be true? Okay, so So 90% said this is false, and you're right. So why is it the case? Well, in order to make this to be true, P and Q must be false. There's no other choice that you can do. When P and Q are false, then P or Q is false. Right? There's no way that you can make this set to be satisfied. But the only hope was when P is false, Q is false, this could be true and true. But if you do that, P and Q are both false, then the disjunction is false. So you cannot find it. Okay? Or if you, the naive idea is, of course, you can enumerate all four interpretations and check it. Okay? What about this one? Is it satisfiable or not? It's true? So what is the interpretation? P to be true? P to be true, Q to be false, right? So then what do we get? True or false is true, and false or true is true. So these are fine. So if they are different, for instance, P is true, Q is false, and this is satisfiable. So this is satisfiable. What about this guy? Is this satisfiable? Let's do this Socrative. Is this satisfiable? Okay, so the answer is true, right? So you can argue this way. These two formulas has to be true, right? So then P must be false and Q must be false. In that case, P implies Q is also true. So this interpretation makes all three formulas to be true. Done. And that's actually the only one interpretation that makes to be true. Okay, so the next one is the notion of equivalence. So we say F is equivalent to G, and symbolically we write this way, the double side arrow. For every interpretation I, their truth values are the same. Their valuations are the same. Okay? So when you write the truth table, okay, the truth table for F and truth table for G, they are identical. When one is true, the other is also true, vice versa. Okay? It doesn't mean that all of them must be true or false, but both of them should agree on the truth values. When one returns true, the other should return true. When one returns false, the other returns false, and vice versa. In that case, we say F is equivalent to G, and this is actually equivalent to saying that this formula is a tautology. Okay? All right, so which formulas are equivalent to each other? Let's choose all. So meaning that when you apply the interpretation, okay, they return the same truth values. Okay, among the 1, 2, 3, 4, which are equivalent to each other. So again, you can think about which one is easier, to find that they're equivalent or they're not equivalent. If they're not equivalent, all you need to do is to find one interpretation that differentiates these two formulas. Okay, so one interpretation that makes one formula to be true, another to be false. Okay, or vice versa. Okay, so let's see. So a bit diverse answer. 1, 2, 1, 1, 2, 2, 3, 1, 2, 4, 1, 3, 4, 1, 3, 2, 1, 1, 4, 1, 4. Yeah, so one is more mostly repeated, maybe followed by 4, but also 2 and 3. So I cannot really say the pattern here. So let's look at this together, which are equivalent. The first formula, both of them are actually tautologies. So P implies Q implies P is a tautology that we saw before, and P or not P is obviously a tautology. So tautology returns true for all rows. So this is actually equivalent. Okay. Now the next one is a bit tricky. Okay. So are they equivalent? So what if we say P is true and Q is false? Now, wait, somebody say, well, I don't have any Q in the second formula, so why should I worry about Q? Well, by definition, interpretation is a function from the signature to truth values. And signature is a set of atoms that you can use in the formula. Doesn't mean that you have to use all symbols in the signature in the formula, right? You can use some part of it. So if I evaluate this P, I can also say that PQ is a signature. So PQ is P equals true, Q equals false is an interpretation that we can apply. And if you apply this interpretation to P, obviously this is true, right? P is true under the interpretation that P is true and Q is false. I don't care about the Q. However, I should care about Q in the first formula because Q is mentioned there. And as you see that this is actually true implies false, which is false. And again, P is true, so true implies false. The first one is false under this interpretation. Second formula, P is true under the interpretation. So if you apply this interpretation, you will see that these two formulas work differently. Okay, the first formula returns false, the second one returns true. So this is not equivalent. Okay? Okay, and the third one, P implies Q is never equivalent to Q implies P. We did something like that earlier in the semester. And you can easily check maybe true, so same interpretation actually, P equals true and Q equals false here. So P implies Q is P equals true, Q equals false. P implies Q is false, right? What about Q implies P? False implies true is now true. So if you apply this interpretation again, you see they are different. Okay? What about the last one? What is the interpretation for bottom? I actually didn't say that. But bottom is always false, regardless of which interpretation that you apply. So all the rows in the truth table, bottom will return false. This is absolute falsity. What about this? Wait, so let's say if P is true, Q is false. Again, the same interpretation. What happens? Well, P is true, Q is false. That makes this to be false. And false implies anything is true. So if I apply this interpretation, the left formula is true, the right formula is false. So they are not equivalent. Okay? Now, equivalence is actually a very important notion because that tells you how to simplify the formula. Okay? In some branches of mathematics, all you need to do is just simplification. When you do the algebra, you have given the polynomial equation. And in the end, what you are doing is solve for x. X equals some value. And what you are doing, all this process is just a simplification. Okay? And what method that you use? You use a lot of algebraic property, law of some exponent, and so on and so forth. You simplify it. Similarly, in logic, you can write something in a very complex formula, but you can also write in a simple way. And you want to check whether these are actually doing the same thing. Okay, this is called equivalence checking. Okay? So it's actually good to know those kind of equivalent formulas so that you can easily manipulate. Okay? So one of the well-known things that we actually saw from the natural deduction is P implies Q is actually equivalent to not Q implies not P. Okay? And P implies Q is actually same as not P or Q. And P implies Q's negation is same as P and not Q. Okay? and P and Q implies R is equivalent to P implies Q implies R. Now, if I ask you to prove why they are equivalent, okay, what you can do is to draw the truth table, okay, and show that all the truth table, they coincide. Okay? At this point, I don't want you to use natural deduction because the definition of equivalence is not in terms of natural deduction. Equivalence here was defined for the interpretation. Okay? Don't try to use natural deduction. We'll get back to that when we have covered soundness and completeness theorem. Okay? So for the next class, I want you to do these two problems. Okay? If somebody can volunteer, I'll appreciate. So these are the questions. So the first question is, this conjunction can distribute over disjunction, and disjunction can distribute over conjunction. So how do we know that this is true? But also note here that the next question is, does disconnective distribute over equivalence? So what I mean by that is, suppose I change this to the equivalence, okay? Does it work? Actually, this one. Okay, can this be distributed over equivalence? Okay, so you can check it. The next question is about proving the De Morgan's law. Okay, another thing is, what if you have the form? So what is De Morgan's law? De Morgan's law is actually basically moving the negation closer to the formulas inside. Can you actually do the same thing when this is actually conjunction or disjunction? Okay. Or can you even do that when this symbol is an implication? Okay, implication or equivalence. Can you actually move the negation inside this parenthesis? Okay, so those are the challenging questions that we'll discuss next class. Okay? All right, so let me finish up here. And let me open the Socrative.